So hello, everybody. Thank you for joining us again for today's Pharmaversity podcast. Very great to have you here again. And today I'm especially excited for our topic. We have our particle control expert, John Beckran, with us today from Pennsylvania. He is going to take us on a journey of the microscopic world of particle reduction measures in the production process of ready-to-use primary packaging containers. So welcome, John. Good to have you here. How are you today?
Hello, Anna. Thanks for inviting me. I'm doing great. Yeah, I'm looking forward to our topic today.
Great. Same here. So we've got a wonderful day today for recording. And since we haven't spoken in person for quite a while now, it's good to at least have you here on the phone. But first things first, we have met in person before, but maybe our audience hasn't met you before. So would you mind to just briefly introduce yourself to the audience?
Sure. My name's John Berggren. I've been on the bench as a bench chemist starting in 1985, working in an environmental lab. I've been in the industry, I guess, 35 years now. And to understand what I do today, my background, I think, is important. I spent about 10 years making tablets for several different companies and 14 years managing and ensuring the quality of parenteral drugs. In parenteral drugs, I ran several different departments, and it got me heavily involved into process management and particle control programs. I've been fortunate enough to work and train under several industry experts as we kind of unpack these particle control mechanisms, particle control programs. I was given the opportunity to build a particle control program for SHOT about 3 years ago now to create a better understanding of where source contamination comes from, to monitor and control the process, and to develop measures to reduce the risk of particles in our final product presentations.
Thank you. So today you're the master detective in particle detection.
Around the office, I joke that everybody calls me Dr. Particle. In the hallway as they walk by, hello, Dr. Particle. Yeah, so it's what I do, it's what I think about, yeah.
Makes sense. You're the one. So we do have a lot of content to cover today, so let's get started right away. I already mentioned that today's topic is going to be all about particle, or better, the absence of those. And in Pennsylvania, where you're based, you're greatly involved in the production of ready-to-use primary packaging. And here containers are washed and deperogenized. That's a tough one for me, I'm sorry.
Depyrogenation process. Yeah, that's the way we remove any bioburden from the product. Exactly. Prior to sterilization, yes.
Thank you. Afterwards, the containers are packed and sterilized, and then the product is delivered to the customer, where it's unpacked and filled, of course. So how does ready-to-use help reduce particle creation in the fill and finish process of pharmaceutical companies?
Well, for one, the nested packaging keeps vials separate from each other. So it reduces glass-on-glass contact, which is a source of a majority of the defects on glass products, as long as you have controls throughout the rest of the process. Each vial has the same experience. It sees the same forming equipment, the same annealing, the same washer, the same depyrogenation tunnel. And that stabilizes and standardizes. And you have one product in the end, and each vial saw the same journey. So standardization is a big advantage here. Mm-hmm. In standard bulk filling, containers face two different situations. Impacts that can affect the physical structure that can lead to defects, and of course, particle contamination. So first, let's talk about glass-on-glass contact. If you ever watch the process, a standard filling line involves loading the glass vials on a loading table into basically a linear feed that loads a wash process. And then separately, as the vials exit the washer and into the depyrogenation tunnel, there's another possibility that glass is touching glass within the depyrogenation tunnel. This can be affected also by downstream processes. So the washer and the depargination can get backed up by issues on the filling end. So the liquid filling of these vials, and then the stopping process creates a backup, and now vials are sitting there on accumulation tables bumping into each other. So think of it this way. When you stand next to a washer or a filling operation and you hear glass, that high-pitched ringing glass on glass, or even the tick, 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 tick of glass vials as they enter a linear feed, you're creating defects. You're creating particles, you're creating checks, you're creating potentially scratches. And sometimes the speed of the line actually poses greater risks because there's more glass moving faster.
Mm-hmm.
So with Adaptic, it's possible to perform the entire fill and finish process within the containers while they remain in the nest. So working with the machine builders, we hand a product where the liquid filling is done within the nest. The vials are never in contact with each other. They're never offloaded and then reloaded, so to speak. And then the stopping can occur also within the nest. So that significantly reduces glass on glass contact and subsequent particle generation. Now, washing and depargination also have an impact on glass. And these processes vary site to site, filling line to filling line. With Adaptic, the washing, the depargination, the support utilities, the compressed air, and the water systems are all standardized. So every vial was ran through the same process. At SHOT, we established a deep knowledge of our process through environmental monitoring and cleaning programs. And we can easily identify things that are happening because we pay a lot of attention to the product. It's easy to identify things like mechanical wear of belts or impacts of rails. Any particle that we identify can be traced back to its source.
Okay, so that leads me right to my next question. So I understand that ready-to-use provides a higher product quality due to closely monitored and standardized production processes. Now, you just mentioned incoming material as well. So I assume you're referring to packaging materials such as top and nest materials, as well as lidding and bagging material.
That's right. Yeah, all incoming materials. So all the materials used to produce the product and then all the materials associated with the packaging.
That makes sense. So these materials, which are required to keep containers sterile during storage and transport, might actually introduce new sources of particles to the product.
That's right. That's why it's important to partner with the right supplier. Particle-free aseptic filling in general is incredibly challenging. In my experience, every step of the process poses different risks, and each is a potential source of contamination. If you consider extrinsic contamination, it's not only the process itself, but it's contaminants coming into the process on the materials and the equipment and, of course, the operators. The possibilities are almost limitless, the particle types that you would find.
I bet. So I remember the last time I tried to apply a new protective cover to my mobile phone, and it was really difficult to ensure that no dust gets caught between the screen and the cover. So I guess here I'm only concerned about the real big parts of particles, the visible ones that would actually interfere with my screen usage behavior. But here we're talking on a different scale, right?
Yes. Well, that's a very good comparison. You're trying to place the screen in an environment that's not controlled. That's a perfect example. Think of that on an entirely different scale, visible and subvisible particles. That's what we face in pharmaceutical filling operations. And anytime you're in Lebanon, feel free to bring your protective cover for your phone, and we'll put it on in my laminar flow hood, and you'll see. With wearing gloves and the impacts of that, it's relatively simple to control particles for that. So, when I started at SHOT, one of the first things that I did was collect materials within the building and create a master particle database. We call it the particle library. And it's still growing. Right now we have over 600 different materials. So what does that mean? We go around and we monitor everything that could be a potential source. So anything that the product contacts, any belts, rails, and so forth, all the materials that are used to produce the bulk component vials are all in this database. When you've gathered and cataloged all these materials within your facility, it makes identifying source contamination that much simpler, because the contamination is typically coming from one or a couple of those materials. I want to challenge you here. Give me an example of some material that you feel we use in vial manufacturing.
Okay. So this is quiz time. Cool.
Yeah.
How about pellets?
Yes. We have a couple different kinds of pallets, and those are in my part.
How about shrink
another?
wrap?
Okay, so bulk vials are sometimes packaged in shrink wrap, and of course, there's some risk that shrink wrap could transfer and be moved around the room. So yes, of course, it's in the database.
Perfect. So we already talked about nest tubs, bags, Tyvek, all the materials.
All the packaging materials for the product.
Yeah. How about the protective clothing that the operators wear?
Well, not only do we have those materials in the database, but we also monitor those materials regularly. So we know what the gowns are made of, the hair nets that they wear underneath, the shoe covers that they wear underneath, the gloves. I've tested 7 or 8 different kinds of gloves, lots of gloves. And again, if these are a potential source or they transport secondary contamination, we want to know about it.
Exciting. This is a fun game.
Yeah. Well, what's interesting is I have, if we're talking about what people, operators, which are a real potential source, or even the tertiary packaging like cardboard boxes, these can transport things that you would never think of. I mean, I have 3 different kinds of cat hair and dog hair and rodent hair and insect parts in the database, because if I ever came across it, I want to know, right? We do incoming inspection on the packaging materials themselves regularly with every lot. And it really helps us identify what the risks are using these materials. It also helps us evaluate and give feedback to our suppliers. It goes down to a level, I can tell you, I joke with my team here, I can tell you what sports team the person at one of my suppliers cheers for, based on the color of fibers that may be on parts.
Really?
Before the execution of these programs. Yeah. I can tell you whether it's summer or winter based on whether they're wearing wool or fleece, or is it lighter clothing. Mm-hmm. This all sounds like fun, but it's actually a really critical step in understanding particle control. By knowing exactly what kind of particles we can find, we can go back to our suppliers, for one, and ask them to fix these sources and provide them with solutions for fixing these sources. Maybe it's control measures in their gowning room, for example. If we find loose fibers on the pre-cut Tyvek sheets that we use to seal the tubs, we can draw conclusions from that maybe their die cutting tools are running a little dull. And remember, where we cut the Tyvek is a potential source of particulate contamination on that material. With that same precision, we can evaluate our own processes. If monitoring behind of or in front of our cleaning programs can tell us something. So think of it this way, what the impact of our cleaning programs are, any shed particles from the cleaning programs, we would know what those are monitoring immediately after we clean. But are we cleaning at the appropriate frequency? The only way to know is to monitor just before you clean. And then we go after the sources and we can fix things. It's relatively simple to identify your most common sources of contamination, and that's what we try to fix first. And now I've been at it 3 years, so now we're really talking about very, very clean processes.
I can definitely see why they call you Dr. Particle now.
So I love doing science. Yeah.
Perfect. So is the degree of detail you pay to particle analysis, is that a common degree, or do you think you go above and beyond of what's standard procedure?
Well, to be honest, I don't think so. I've worked with only about 3 people that get super excited about this, where they're walking and talking particles and isolation techniques and contamination control programs in general. Over the past years, we established a deep knowledge of our processes as a result. We use these inputs to make changes to cleaning programs and preventative maintenance programs. There's an old saying that says that the product will always tell you what's wrong, but it's already too late to do something about it.
Okay.
So in the end, the process can tell you its secrets if you know what questions to ask, and you have analytical techniques that allow you to get to the root cause very quickly.
Makes sense. So with that brings us directly to your latest study.
Yeah, so I want to focus on one study as an example of some of these control programs. I think as we have further opportunities to talk down the road, we can talk more about the layering of these systems. In this study, we evaluated particle generation that can occur when the customer peels and removes the Tyvek sealing lid.
All right. So tell me, what exactly did you test?
So as a sealing material, the industry leader for drug and medical devices is DuPont Tyvek. Tyvek is a strong, breathable polyethylene material. It has a fantastic antimicrobial barrier. They have a very low risk of shedding, as long as you don't mess with it, as long as you don't stretch it, as long as you don't cut it. You can imagine it as a sheet of basically what was cotton candy compressed into a thin layer. These long interlinked fibers are bonded via compression, and they're very stable. The problem is once we apply an adhesive and then we cut them into small rectangles and then put enough strain or stress when we peel it, these materials can shed particles. So just imagine over open containers, you have a fibrous material that contains an adhesive. That's the study we wanted to better understand. So for our study, we focused on particles released by the removal of that Tyvek sealing lid. We evaluated Tyvek combined with 6 adhesives in the first pass study. These adhesives were from 2 formulation categories, if you will. Hot melt glues and water-based glues, so like a PVA type glue, to see which is the cleanest combination available to the industry.
Okay, so we've got an industry standard lid material, a wide selection of glue attached to the lid and to the tub, and you tested how these Tyvek glue combinations performed in regards to shedding during the process of opening the tub at the filling line, correct?
Exactly. We wanted to focus on the particles released into this critical environment, right? This is immediately prior to the filling of these vials by the removal of the sealing lid, and any impact, if there is any, by the selection of the glue. All other factors were kept constant. Now, there are many ways to remove the lid. I want to say up front that we decided in this study to pick one of the worst methods of removing the lid that's possible. Let me explain. When we peel the Tyvek off, if we peel it at room temperature at a very, very tight angle, like let's say we peel it directly back on itself at 180 degrees, you can imagine the Tyvek, the cross section of the Tyvek, like a grilled cheese sandwich. I use that analogy internally quite a bit. So picture the cross section of the Tyvek. You have 2 layers of bread, which are a higher density material, and then an inner layer that's a little bit less dense. And it has to do with the compression that happens of that cotton candy to make the Tyvek. The cheese on the inner section of the sheet is a little bit lower fiber density than the 2 outer layers. Now, as these 2 slices of bread are pulled in the same direction, and you pull it at a hard angle, so you're pulling it directly back on itself, you create a lot of stress between the layers of the sandwich. The inner layer of Tyvek, the inside of that curve, is really being compressed and squeezed, where the outer layer is stretched. And now the outer layer is where we have the adhesive applied. So we're stretching and pulling technically the fibers apart and opening space on the outer layer where the fibers are stretched. The result is you create a lot of stress on the Tyvek. And possibly, using the grilled cheese sandwich analogy, maybe many crumbs of glue. You most likely have to vacuum your kitchen floor after this one. So with any other material, it would be very similar. Just in this case, we're not talking about large crumbs, but Tyvek fibers and small adhesive particles. That's the risk in this system.
I understand, and I think I will never forget the grilled cheese sandwich ever again. Because I understand, of course, the crumbs, or in this case, the fibers and particles, that's definitely not what we want to see.
Yeah, no, absolutely. But we do need to know. And remember that this represents a worst case peeling scenario. It may be different depending on the filling line manufacturer if you peel the Tyvek differently. And a lot of filling line manufacturers do have intellectual property around how they peel the Tyvek. They apply some heat to soften the adhesive. They apply much more heat to melt the adhesive. You can peel at lower angles so you don't compress the bread, if you will, from the grilled cheese sandwich, right? So if you peel it at a higher angle, like a 90-degree angle to the seal surface, you create less stress within the Tyvek. And you'll see these variations within machine builders.
All right, makes sense. So for your study, what did you do next?
So in this study, we performed all the testing under a standardized condition. Okay, we performed a sealer qualification on all of the adhesives, and at a minimum, we tested 40 tubs each of each glue type. So with each test, we had 40 tubs. So it was a complex study and a lot of testing because we wanted to better understand some of the statistics involved. The sealer qualification was standard seal integrity, so dye penetration and peel forces and seal inspect. Okay, so after we sealed these tubs for the study, we let them sit to represent standard processing. And now the lids were manually peeled, as I said before, at a 180-degree angle, directly over a particle counter. So the MET1 particle counter that we use to monitor the clean rooms, if we remove the Tyvek lid directly over it, I have to create a special cycle. So the cycle basically ran a purge up front to monitor the air quality in the environment before the test is started. And then we had some timing of the cycle to pull a lot of air timed with the time it took to remove the lid. So airborne particles were generated during the process, collected by the system. Now separately, the tub and Tyvek seals surfaces were evaluated in a different manner. We used a contact adhesive roller, similar to the fiber roller that you would use to clean your clothing if you have a pet. And what we did was, after we peeled the Tyvek and after the particle counter finished its cycle, we would use a contact adhesive roller to roll these two materials and look for fiber artifacts or adhesive artifacts.
All right, so that was the study design. What were your findings?
So the first pass study showed significant variations, like you'd expect, in particle generation from the different adhesives. There was even 2 orders of magnitude higher shed particle counts of specific adhesives over some of the others in the study. The first round of testing demonstrated some worst case combinations, and because they performed significantly worse than the others, we eliminated those from the next step of the study, which was basically to repeat the study again from scratch using the 3 leading candidates. And then in this step, we also evaluated the performance of the 3 leading candidates, both pre and post sterilization. Now you have to keep in mind, the customers receive product after sterilization. In this case, we wanted to evaluate any impact of the sterilization. We wanted to better understand the shedding behavior of the Tyvek and the glue combination and any impact of the sterilization cycle. So we take the lead candidates and we perform a second phase, basically repeating the first phase pre-sterilization and then doing the identical test after sterilization to see if there's any degradation of the glue. The hypothesis was that we might have some cross-linking of the adhesive or some degradation of the adhesive bonds, which looks to be the case, actually. So the 3 best performing glues from the first round were prepared again, sealed again, and then basically challenged pre and post sterilization. And there was a lot of interesting information that we gathered.
So from what you're saying, you identified a clear winner among the tested glue types?
Yes, the best performer had a combination of low airborne shed particles with relatively no impact from the sterilization cycle. So low, I call it labile particles or fiber artifacts left on the tub or on the Tyvek. We also learned it's very important to keep the sterilization process in mind. What was interesting in the study to me was the particles on these materials, on the Tyvek and on the tub seal, using the contact adhesive roller, actually went down after sterilization. And separately, the airborne particles went up, but on certain formats went up much higher than others. So the lead candidate had a combination of low shed airborne particles. And again, using a contact adhesive roller, the 2 materials, the tub and the Tyvek, actually contain less labile particles on the surface after removal, which could technically contaminate the environment where the filling operation is done. And the tub, let's face it, goes on sometimes as secondary containment deeper into the process. After stoppering, it's used to stage and hold on to the product. So we don't want the tub contributing particles to downstream processes. So this was really important and actually really interesting.
So after your study, did you end up changing the adhesive type used for adaptic ready-to-use vials?
No, we didn't. The adhesive that we were currently using was the best performer in basically all elements that we evaluated.
Wow, well, that's a good result then. So, long story short, thorough testing leads to optimization within the production, which ultimately ensures a better and safer product to our customers, if I try to wrap up what you just explained.
That's right. And a better understanding of our product. And as I mentioned earlier, this is only one of many factors that can affect particle loads. We have a lot more information about our product and our processes that we've already studied. And I like to say it's all on our radar. Our next study is already in preparation for publication. And here we focus on the selection of the materials that we use to make the packaging materials. So the selection of resins that we use to make specific components that are used to present the product to market.
All right, so much more to come. So speaking of studies, the first study you already mentioned earlier of this series, it will be published already this July. It'll be in the Labag magazine for everybody in the audience who would like to go back and learn some more and probably even take a look at the figures and tables of John's finding. And that's actually by the time we're recording today. It has not been published yet, but it should be available early July. So please feel free to take a read and learn more about the topic.
That's right. And the second publication is already written and submitted and scheduled for publication in Q1 2021.
Yes, that's correct. And from listening to you, I believe that there might be even more to come after Q1 21. So wow, that was quite an intense session today. I, for my part, have learned a lot, not only about grilled cheese sandwiches and cotton candy, but also about how to keep my cell phone screens clean and to apply them correctly. So very, very interesting. I hope our audience learned just as much as I did. John, thank you so much for taking the time to being here with us today and for elaborating on your latest study. It was really interesting.
It's my pleasure. Anna, thank you. And can I just take just a second to thank my team that's been
Of course.
supporting this project, including Denise Rachel, who put together a lot of the data for this study. I work as part of a really fantastic group, and I want to give them credit for all the work that they're doing.
Of course. No, I bet they're looking forward to that. I will let you know once the podcast is online so you can share it with them as well.
Thank you.
Well, it's been so great to have you here. Thanks again. Goodbye to everybody listening to us, and we're looking forward to the next podcast session where you can hear us again.
Thank you, Anna. Have a great day.
You too. Bye bye.